We get a look at the binomial theorem, and I love this theorem because there's so many patterns to it, and that's what I want you to do. I want you to look at these patterns and see if you can figure out some of them on your own, and then we're going to apply it. So first of all, the binomial theorem is taking a binomial and raising it to a power. So remember, a binomial is a polynomial with two terms. So like x plus y, that has two terms. 2x minus 7, that's a binomial. 3y plus 7z, that's a binomial. So we're taking binomials and we're raising them to a power. So I have several of them written down here, and I just took something simple like an x plus a y. So you notice, see our binomials in here, x plus y, x plus y. Those are binomials, and we are raising them to different powers. So we start off with raising it to the 0 power, and then the first, and then the second, and the third. So we have binomials raised to powers, and we want to look for patterns embedded in here. Well, we know that anything to the 0 power is 1, so x plus y to the 0 is just plain 1. We know that anything raised to the first power is itself, so here we're just going to have x plus y. To get x plus y quantity squared, we would take x plus y times x plus y, and then we would do the double distribute. So we'd have x squared plus xy plus xy plus y squared. So we get x squared plus 2xy plus y squared. So this is x plus y quantity squared. And those of you that still take this binomial and square it, and you get x squared plus y squared, you need to stop doing that. We always have a middle term. So remember that. Don't make that little mistake over and over again. So if I take an x plus y and I raise it to the third power, I take my answer that I had before here, which was raised to the second, and multiply it by another x plus y. Well, anyway, we get this guy when we do it. And then if we take that answer times another x plus y, so see how the pattern is growing? Well, let's take a look at some of the things that are occurring. When we have it raised to the first power, notice how it goes. From 1, the first term here is x. The first term here is x squared, x cubed, x to the 4th, x to the 5th. Well, that's a pattern right there. So if I were going to take x plus y and raise it to the 6th power, could you tell me what the first term in that expansion is going to be? Well, you certainly could. It's going to be x to the 6th power. Now, could you tell me what the last term in the expansion is going to be? Well, it looks to me like it's going to be y to the 6th. There's another pattern. Okay? Take a look at this pattern. Notice how we have an x to the 3rd here and a y to the 3rd here. X to the 4th, y to the 4th. X to the 6th, y to the 6th. And then if we just go one in, notice on this one, this next term, I went from x to the 5th on the first term to an x to the 4th, to an x to the 3rd, then an x squared, then an x, and then in the very last term there's not an x at all. So the x's are decreasing by 1, and at the same time the y's are increasing. So I don't have a y here, y to the 1st, y squared, y cubed, and that is increasing. Okay? Another thing I notice is that, look at the coefficients. So let's go up to this one, and I'm going to look at the coefficients of the expansion. So I've got a 1x squared, I've got a 2 xy, and I've got a 1y squared. If I look at the coefficients of this expansion, I have a 1, a 3, a 3, and another 1. Look at the coefficients of this expansion. 1, 4, 6, 4, 1. So another pattern is the symmetry that you see in there. So on the one that's raised to the third, we have a 1, 3, 3, 1. So if I read it backwards, I'd get the same thing. On this one here that's raised to the fourth, I have a 1, 4, 6, 4, 1. If I read it backwards, it'd be the same thing. So notice the pattern there. So there's just so many patterns here. So let's take a look at what the binomial theorem says then. If we are taking a binomial and raising it to a power, then here's where it's showing some of those patterns. It's saying your first term is going to be the first term in your expansion raised to the n. So the first term is x, so I'm going to have x raised to the n. And the very last term in the expansion is going to be the y to the n. So if I have x plus y to the 9th, I know that I have my first term is going to be x to the 9th, and my very last one is going to be y to the 9th. So that's just one of the patterns that we saw before. Okay, if you look here, and it kind of gives you a sneak peek at the pattern of getting the coefficients. And one way, you see on this first term then, you have, it says take the n, which is your exponent on the first term, times the variable to 1 less power. So let's say that we had x plus y to the 4th. So from the pattern, it looks like the first term is going to be x to the 4th. And the next one, I'd take that exponent of 4 and move it out to the front. It becomes a coefficient. And x then is raised to 1 less power. And then we'd have a y. And it starts growing that way. Now the next coefficient gets a little bit more difficult, and there's a little bit of a pattern in there. So it's a little bit easier then to think of the coefficients as combinations. And you studied combinations in probability, and you did quite a bit of this in geometry and then in Algebra 2 again. So a combination is where the order doesn't matter. So let's say that I am going to get a pizza. I'm going to build a pizza, and I go to Pizza Hut, and they have 11 ingredients, and I want to know what's the number of pizzas I can have that have 2 ingredients. Well, it doesn't matter if they put on the pepperoni first and then the black olives. It's still going to be the same thing, so the order doesn't matter. So that's what that capital C stands for. So combination, if we were at Pizza Hut and they had 9 ingredients and I wanted to make 2 different pizzas. So I can use that to get those coefficients. So a reminder then of what that formula looks, or how you evaluate that formula. It says is you take n factorial, so ours would be 9 factorial over n minus r. So the n is the 9, the r is the 2, n minus 2 is going to be 7 factorial over the r factorial. In our case with the pizza and the 2 ingredients, it would be 2 factorial. So to evaluate that then, 9 factorial is 9 times 8 times 7, 6, 5, and so on, all the way down to 1, over 7 factorial times 2 factorial. Well, what happens then when you're multiplying is that all of these reduce from 7 on down. So I actually end up with 9 times 8 over 2 times 1. And I can even reduce by 2. So I just have 9 times 4, or 36. Okay, so there's the formula for the combination. And we'll come back to that in just a little bit. I also want you to know that sometimes in this book, instead of saying combination and a subscript of 9 before and a subscript of 2 after the C, sometimes you will see it written as this, a 9 over a 2 in parentheses. So those two mean exactly the same thing. So that is a combination. Okay, so using our formula, let's see if we can find these combinations. So A says find combination 8, choose 2. So here's our formula up here. The first value is the n, so we have 8 factorial over 8 minus 2, or 6 factorial times 2. Well, this time when I expand it out, I know that from 6 on down is going to cancel out, so I'm just going to write the numerator as 8 times 7 times 6 factorial, which is 6 times 5 times 4 all the way down. And then I already have a 6 factorial here times, whoop, I forgot my 2 factorial, times 2 factorial. Well, the 6 factorials cancel. 2 factorial is simply 2 times 1, so I'm going to reduce the 2 into the 8, so I need 4 times 7, so we should get 28. Okay, for part B, 10 is the n, so I need 10 factorial. 3 is the r, so I need n minus r, so it's 10 minus 3 is 7 factorial times r factorial. Okay, so I'm going to write this the 10 factorial as 10 times 9 times 8 times 7 factorial. I'm going to stop with the 7 factorial because I have a 7 factorial in the denominator. That will cancel. So the 7 factorials cancel. 3 factorial, however, is 3 times 2 times 1. So I'm going to reduce the 3 into the 9. And I think I'll take the 2 into the 8. So everything is gone in the denominator. In the numerator, I have 10 times 3 times 4. 3 times 4 is 12, times 10 is 120. Okay, and then the last one, combination 7, choose 0. So the formula says take 7 factorial over 7 minus 0 factorial times 0 factorial. Well, 7 factorial will cancel out. 0 factorial is 1, so this is 1. So why would that be 1? Well, let's say that we go into the pizza place again and they only have 7 ingredients, and we want to know how many pizzas can we make that don't have any ingredients. Well, we can't choose any of them. There's only one way to do that. Okay, so that's why it's equal to 1. All right, let's move on then. Another way to get the coefficients of the binomial expansion is using Pascal's triangle. And this was named after a famous mathematician who lived a long time ago. But this triangle has all kinds of applications. And the triangle begins with a 1, and then the second row has 2 1s, and then we get 1 2 1. And the way you build the triangle is you add any 2 consecutive numbers on the diagonal above it. So here, to get this one, we'd add the 1 and the 3, so we'd get 4. Add the 3 and the 3 to get 6. 3 and 1, and then we bring down a 1. So this next row would be 1, 5, 10, 10, 5, 1. The next row, so notice the symmetries there, and those are the exact same symmetries that we're seeing in the expansion. I'm going to do one more. Okay, so in general, the nth row in Pascal's triangle gives the coefficients of x plus y raised to the nth. So if I wanted x plus y, let's do the simple one, let's do the squared. Remember, we get 1x squared plus 2xy plus 1y squared. And we usually don't show those ones in front of the x squared and the y squared, but the coefficients are still 1 whether we show them or not. So we've got 1, 2, 1, and notice how that is the same as this row. If I take x plus y and cube it, I get 1x cubed plus 3x squared y plus 3xy squared plus y to the third. So my coefficients are 1, 3, 3, 1. That corresponds to this row. So if you don't have to go too far down, then it's fairly easy to use Pascal's triangles to get those coefficients. All right, anyway, let's try and pull it all together, and let's come up with how do we then expand. Let's go with a plus b to the 4th power. All right, so we're going to use well, you can use the binomial theorem. I'm just going to look at kind of the patterns that we saw. So we take, the first term is going to be a to the 4th. In the next term, I'm just going to leave the coefficient blank for right now. But I know a is going to be to 1 less power. Now, and as a decreases, b starts increasing. My next term then, a is to 1 less power than the preceding term. B is to 1 more. Then a is going to be to the 1st, b to the 3rd. And in the last one, I don't have an a anymore, or you can think of it as a to the 0, and b is to the 4th. But I want to stop with the b to the 4th. Now the coefficients, if you go back to Pascal's triangle, you would see that the 4th row, the coefficients are 1, 4, 6, 4, 1. So I have to start way over here. So 1, 4, 6, 4, 1. Another way to get those is to use combinations. Okay, so here this is going to be combination 4 choose 0, combination 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay, so for example, let's just take this one. Okay, using that formula for the combination, it says you take the n factorial over n minus r, so 4 minus 2 factorial, times r factorial. All right, when we simplify that, 4 factorial, 4 times 3 times 2 times 1, 2 factorial twice. So I'm going to reduce by a 2, reduce this 2 into the 4. 2 times 3 is 6. That is another way to come up with that coefficient. Okay? So that is the binomial theorem. So it is a quicker way to take a binomial and square it instead of going a plus b times a plus b times a plus b and writing that out and expanding it. All those times. That's just not as much fun as finding the pattern and then using that pattern. All right, let's try this one. So we want to take now, instead of an a plus a b or an x plus a y, we've got to remember that this 2x now is going to be our whole x. Okay, and what I mean by that is we're going to start with our first term is the 2x quantity to the fourth. And then we still have a coefficient out to the front, plus the coefficient times 2x to 1 less power. At the same time, then, the 3 is increasing. But because of this negative, we also have to include that negative with the 3. So we're going to think of it as a negative 3 to the first. Then our next term, the 2x is going to be to 1 less power, so it's going to be squared. The negative 3 is increasing. The 2x is now raised to the first. The negative 3 to the third. And then in the last term, the 2x is raised to the 0, or the 2x is completely gone, and we have the negative 3 raised to the fourth. And remember the 4, it's that very first exponent on this term, and it's the very last exponent on the last term. Another pattern in the expansion is that if it's raised to the fourth power, we actually have a total of 1, 2, 3, 4, 5 terms. If it's raised to the third, we'll have 4 terms. If it's raised to the 8th, we'll have 9 terms. Okay, so it's raised to the 4th, so we have those 5 terms. Now we have to plug in the coefficients. We just did the coefficients on the last one, and we used Pascal's triangle, and those coefficients, we'll use the same ones, 1, 4, 6, 4, 1. So now what we're going to do is just go back and simplify. So let's just take a look at the first term here. The first term says we have to take 1 times 2x to the fourth. Well, to take 2x and raise it to the fourth, both the 2 and the x are raised to the fourth power. So 2 to the fourth, 2 times 2 times 2 times 2 is 16. And then times the 1 on the outside will give us 16x to the fourth. For the second term, so we want to take 4 times 2x to the third. So 2x to the third means we take 2x times 2x times 2x. So that gives us 8x to the third. So remember, 2 has to be raised to the third also. 2 times 2 times 2 is 8. And then I also have another number here, the negative 3. So now, when I combine all of that, I just go ahead and take all of those numbers. So I take the 4 times the 8 times the negative 3, and I just multiply them all together and put them out to the front. So I get a negative 96, and then I have an x to the third. Okay, let's go on to the next term. It says take 6 times 2x quantity squared. So you're squaring the 2 and the x. So we're taking it times 4x squared. And then I want to take it times negative 3, which is also squared. So negative 3 times negative 3 is a positive 9. So I've got a 6 times a 4 times a 9, which gives me a product of 216x squared. Going on to the next term, we've got 2x to the first is just 2x, Now I need negative 3 to the third. Now remember here, a negative times itself 3 times is going to be a negative. So negative 3 times negative 3 times negative 3 is negative 27. So I'm going to take 4 times 2 times negative 27. And you can double check me. So here I get a negative 216, and my only power of x is just x to the first. And then for the last term, I don't have any x's. I'm multiplying by a coefficient of 1. So I need a negative 3. Make sure and put that negative 3 in parentheses in your calculator, and you will end up with a positive 81. Okay, so notice when I simplify it all, I don't necessarily have the pattern that I had here in Pascal's triangle. So the pattern for the coefficients, you see the symmetry up here, but because I had a 2 and a 3 thrown in there, it doesn't show up in the final expansion. So that's a way to get that. And yeah, that takes a little bit, but you know what? It's still simpler than doing this. Taking this times itself, getting that answer, and then taking that answer times 2x minus 3 again, get that answer, and then take it times 2x minus 3 again. So if you don't like the binomial expansion, your other choice then is to do this. Okay? I personally like the patterns. Now let's take this one. We have a binomial again, so notice this is 2 terms. So an x squared is 1 term plus 4, so there's the binomial, and we're raising it to a power. Okay, so we have a coefficient times the first term, which is x squared, raised to the third. And remember, the 4 doesn't show up in that first term. Then we have a coefficient. Now, as the x squareds decrease in power, the 4 starts to increase because the 4 represents the y. Our next term, the x squared, is to 1 less power. The 4 is to 1 more power. Whoops, so 1 more than 1 is 2. And how many terms do I have in here? Well, if it's raised to the third, we should have a total of 4 terms. I have 1 term here, 2, 3, so I should only have 1 more term. The x squared is gone. The 4 is raised to the third. And yes, there's our first term, has that exponent of 3, and our last term has that exponent of 3. Okay, so now we're just going to simplify each one of those. Now we've got to put in our coefficients. Because it's just raised to the third, a quick way to do it is just Pascal's triangle. So 1, 3, 3, 1. All right, so in this first one, I have x squared to the third. Remember, that is x squared times itself 3 times. That gives us an x to the 6th. So the power to a power rule means we multiplied those 2 exponents together. So my first term is 1x to the 6th. My next term then, I need 3. So right here, I need 3 times x squared squared, so a power to a power, that's x to the 4th, times the 4. 3 times 4 gives us 12, x to the 4th. So that's my second term, all simplified. Okay, now I'm going to move on to this term, the third term. So in the third term, I'm going to take 3 times x squared times 4 squared. 3 times 16 is 48 and x squared. And then for my last term, I need 1 times 4 to the third. 4 times 4 is 16, times 4 is 64, times 1 stays 64. So here is the expanded form of my binomial x squared plus 4 raised to the third power. Once again, if you don't like doing it that way, you could always get that same answer by taking x squared plus 4 times itself 3 times. Okay, let me bring up the next screen. Now what we want to do is find a particular term in a binomial expansion. So there's a formula for that too, but you can also kind of look at the patterns. So I'm going to take you back. Let's see if I can do this without too much hassle. I'm going to take you back to that very first screen for just a second. And where we had all of those powers, oh, it gets kind of messy, it gets out of order here. Let's take where we have the binomial raised to the third power. Okay, so when it's raised to the third power, look at the coefficient on the y term, on the second term. In the first term we don't have a y, then in the second term we have a y to the first, and then a y squared, and then a y cubed. So they keep increasing. Okay. Another pattern is that notice whatever your exponent is, so like here, if I'm raising it to the fourth, on each term, take a look at the exponents. Like here I have an exponent of 2, and here I have an exponent of 2. And when you add them, you get 4. Here on this term, I have an x to the first and a y to the third. When I add those two together, I get a 4. So the sum of the exponents is always going to be 4 if you're raising the binomial to the fourth. There is another pattern. All right, now let's see if I can get back down to that other screen. And I need this one here. All right, so we want to find just a specific term. So like if it says, give us the r plus 1 term. So let's say r is 4. Then the fifth term in the sequence then, so where we're looking for that combination is this number right here. Okay, so to get the value of the fourth term, the r is going to be 5. So on the second term, that tells you what the exponent is. And then this exponent is whatever you're raising it to begin with. Let's say we're raising it to the 8th. So 8 minus 5 would be 3, because it always has to add to 3. Okay, well, that looks kind of confusing there, but maybe if we apply it to this here, it will make a little bit more sense. So to get that sixth term, then we want the exponent on the 2b Okay, so this sixth term, well, if we're looking for, like up here, the fifth term, sorry about that, go away. So I lost it. Okay, so let's try it again. So if I'm looking for the sixth term, then 2b is going to be raised to 1 less power than the term I'm looking for. So this is going to be raised to the fifth. The a then is going to be raised to the third, because the 3 and the 5, those two exponents together always have to add up to 8. And then I also have a coefficient out to the front of it. Okay? And the coefficient is the combination. Oh my goodness. Sorry. Dang it. I keep losing that. 2b. Let's start over. With the sixth term, 2b is going to be raised to the fifth. The a is going to be raised to the third because the 3 plus the 5 has to equal 8. And then for the coefficient, we can use a combination. We could also use Pascal's triangle, but we'd have to go all the way down to the 8th row, and that's a little cumbersome. So I think on this one we'll use a combination. So we have combination 8, choose 5. So these two numbers are the same. Okay? All right, so combination 8, choose 5. So let's use that formula first of all. So we have 8 factorial over 8 minus 5 factorial times 5 factorial. So if we simplify that, 8 times 7 times 6 times 5 factorial. I'll stop with, I look at my denominator and say I have a 3 and a 5. I'll go until I get the largest of those. And I'm just going to switch the order. The order doesn't matter with the 3 factorial and the 5 factorial. But the 5 factorial is going to reduce out. 3 factorial is 3 times 2 times 1. And that we see is 6. So 3 times 2 is 6. So I can reduce out the 6. So left on top, I just have 8 times 7. All right, so the combination 8 choose 5 is 56. Then I need a to the third. But at the end, I still have a 2b to the fifth. So that means that quantity has to be raised to the fifth power. So 2 to the fifth is 32. And then the b to the fifth, we write it like that. So now my last step is to clean this up. So the best way to write that is to go ahead and take the 56 times the 32, and I get 1,792. And then I'll take the a, because it was the first one in this sequence, cubed, and then b to the fifth. Now that is so much easier than taking this whole thing and raising it to the 8th power and looking at all 9 of the terms and then counting over to get the 6th term in it. Okay? So there's the pattern that we can use with that one. All right? Find the coefficient of the term that has a to the 6th, b to the 5th in this expansion. Oh my goodness, look at that expansion. It's raised to the 11th power. So there's no way we'd want to go to all that work. That would just be hideous. So we are just going to narrow in. We're just going to zoom in on the one term. Okay? So if I want the b to the fifth, then that means the negative 2b, that whole thing is going to be raised to the fifth. Remember how these two always add up to this one. So our a includes the 3, so that means the 3a is going to be raised to the 6th. And then we have to do combination. The first number that we choose is 11. We have 11 things to choose from. We want to choose 5. So that's all we have to simplify. So the numerator, or like this, when I simplify this, combination 11, choose 5, then I do 11 factorial over 11 minus 5 factorial times 5 factorial. All right, and then we also need 3a to the 6th. So remember, that means the 3 has to be raised to the 6th power, and the a has to be raised to the 6th. And then we also have negative 2 to the 5th and b to the 5th. All right, so we got a lot of numbers there we're going to combine. So 11 factorial, we're going to go 11, 10, 9, 8, 7, 6. And then 5 factorial is 5 times 4 times 3 times 2 times 1. So when I reduce, let's go with 2 times 5 is 10. I can take a 3 out of the 9, and I can take a 4, reduce it into the 8. All right, so I've gotten rid of all the denominators. So my numerator is 11 times 3 times 2 times 7. So I'm getting 462. So go through and make sure I did that right. I'm just multiplying it out right now with you. Then I have 3 to the 6. So 3 caret 6 is 729. And then I have that a to the 6. And then negative 2, make sure and put it in parentheses. But if I have a negative raised to an odd number, it's still going to be a negative. So think about what the answer should be. So negative 32. And then a b to the 5th. So to get my whole coefficient then, I have to take 462 times 729 times negative 32. So we take all of those factors and put them all together. So times 729 times negative 32. Once again, might be a good idea to double check. Whoops, put that in the wrong place. I'm getting negative 10,777,536, a to the 6th, b to the 5th. So holy cow, I hope that's the right number. I hope you got the same thing. Please double check. Make sure you agree with that. And then it will be your turn. So here are some that I would like you to try before you come back to class. And I hope you have as much fun as I have doing these. And I will see you in class.